Rinku ma'am.
This one. When I start presentation?
Sir, you can check the screen share also.
Okay. Can you hear?
Rinku ma'am. Over to Rinku ma'am.
A very good morning to everyone. I once again welcome you to the concluding day of the 1-week national workshop on advanced synthesis and characterization techniques organized by Department of Applied Physics, Amity School of Engineering and Technology, Amity University, Madhya Pradesh. Today we are honored to have with us our guest, Dr. Rakesh Kumar Pandey. He is Assistant Professor at School of Physical Sciences, Pure and Applied Department of Pure and Applied Physics at Guru Ghasidas Central University, Bilaspur. Before inviting him for his talk, let me introduce him to you. Dr. Pandey has done his BSc, MSc and PhD degree from Rani Durgavati Vishwavidyalaya, Jabalpur. His areas of interest is material science, thin films, optoelectronic devices, optical communication, nanomaterials and devices. He has more than 21 years of teaching UG and PG students and research experience. He is member of number of professional bodies such as life member of Indian Society of Particle Accelerators, member of Indian Science Congress, life member of Luminescence Society of India, Jabalpur Center, member of Optical Society of India. He has published number of papers in reputed index journals and has number of book chapters to his credit. He has written 2 textbooks for BSc students. He is a number of students are enrolled under him for PhD thesis. He has guided more than 15 students for their project in MSc for MSc project, and he is or you can say he has held number of administrative responsibilities like member of BOS Board of Studies, academic coordinator in Applied Physics Department, executive member of Guru Ghasidas University, academic council member of Ghasidas University, etc. I now request Dr. Pandey to kindly deliver his talk. Please, sir.
Yes. Thank you very much, madam, for kind word. Thank you very much. Yes. Can you see, madam? Can you see my this presentation?
Not yet, sir. It
Not.
is kindly share, sir.
You have to share. Share it from here. Now it's okay, madam. It's okay.
Yes, sir. Visible.
Okay. Thank you. Thank you so much. So my today's talk is atomic force microscopy technique. First of all, I'm very much thankful to Manisha madam and Professor Mishra sir, Pankaj Mishra sir, who have given opportunity to present my work over here in this 1-week national workshop on advanced synthesis and characterization techniques. Thank you very much, madam. So, am I audible?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes,
Okay.
sir.
Okay. Okay. So, as all of you know, this in today's era, material science is playing very important role, and our ultimate aim is to synthesize and characterize best quality material for device application. This is the era of communication. We need to have various kinds of devices. We need to design, fabricate, and test them. Not only testing, even we have to integrate for different types of systems. And it requires the various tools and techniques. One of that, atomic force microscope is one of that. For the sake of convenience, I have classified my talk in various contents. Like we will discuss what is AFM, how AFM works, how AFM and STM are different, how this AFM is different than the optical and electron microscope, how AFM works, and we will see what are the various limitations. Since this is the basic lecture, we will also discuss the limitations of the scanning electron microscope and atomic force microscope. And since this AFM, ultimately we need to go for factorial and multifactorial studies, analysis of AFM data. That is called factorial and multifactorial analysis. We'll see it also. I am confused. So first of all, we will discuss what is this AFM, why we need to have atomic force microscopy. So as all of you know, nowadays atomic force microscope is playing very important role. If you will see the history of AFM, AFM was initially developed by Binning et al. In the year 1986, just to overcome the limitations of the scanning tunneling microscope. And basically, AFM, it is a member of this family, the scanning probe microscope family. If you will see how this AFM is different than the scanning tunneling microscope. Basically, what we do in case of scanning STM, we require only conducting materials, conducting samples in STM. The reason, because of its resolution. The resolution in STM can be obtained by using its tunneling current, and this tunneling current produced between the STM probe and the sample surface. This is the reason, that's why we need to have conducting samples in case of STM. Now here there are many samples. We are having one of that, we are having biological samples. And as you know, most of the biological samples are non-conducting samples. So we cannot use STM for non-conducting samples, such as proteins, biological tissues, cells, etc. Whereas in case of AFM, AFM uses small forces on the surface by a probe, that is AFM probe, and it is called tip. And it do not damage the samples. It provides information. So whenever you are synthesizing, fabricating thin films or any samples, or if you are having biological samples, its surface topography can be easily studied by using AFM rather than STM. Now, basically, if you will see, if you will compare the application of AFM for material scientists, physical sciences, and biological sciences, so I would like to say that AFM is more useful for the biological samples, for biological peoples, because there are many things that can be studied by using AFM for biological sciences. So it is said that the biophysical scientists are more beneficial with this AFM rather than physical sciences scientists, because here the resolution in case of AFM can go up to nanometer scale, and 3D imaging possibility can be made by using AFM. Since this AFM, it is the family of STM, scanning tunneling microscope. So let us see basically STM. What is this STM and working of STM? Then we will come over the AFM. So basically STM works by scanning a very sharp metal wire tip. If you will see this diagram of experimental arrangement of STM. So here we have to use one sharp tip and it is made of metal. This is the sample and this is the tip. So this tip is made of metal. Basically it is metal wire. And by bringing the tip very close to the surface of sample, by applying some electrical voltage to the tip or sample, one can imagine the surface at an extremely small scale. So here in STM, we require one conducting tip, and if you will apply some potential across the sample, you can imagine up to very small scale level. You can get the surface characteristic. There are several principles that is required in STM. So one very important principle is quantum mechanical effect. Since here it is called scanning tunneling microscope, so tunneling effect is important. As you know, as students know, the quantum mechanical tunneling. So this quantum mechanical tunneling is required. Here it differentiates classical mechanics and quantum mechanics. So this quantum mechanical effect, this effect allows us to see the surface of our sample. Second one is the piezoelectric effect. All of you know the piezoelectric effect. This is the effect that allows us to precisely scan the tip up to its angstrom level. And one another important technique is there. It is required a feedback technique, or it is called feedback loop. Basically the feedback loop, it monitors the tunneling current and coordinates the current and the positioning of the tip. So when the position will be proper, very easily you can monitor the tunneling current. This is the experimental arrangement of STM. Here this is the tip, and basically this is the sample, and here feedback mechanism is there. And this tunneling current becomes very important over here. So very precisely by using this feedback mechanism, you have to monitor the tunneling current. And if this tunneling current can be precisely controlled, we can scan the surface of our sample specimen up to nanoscale level. This is one another experimental arrangement of STM, how it works. Now here basically, if you will see, mainly the tunneling is important over here. So how this tunneling, quantum mechanical tunneling takes place in this STM. Basically what happened? As you know, tunneling is quantum mechanical effect. Tunneling, basically tunneling current occurs when electrons move through the barrier that they classically should not be able to move through any surface. So here we can also differentiate classical mechanics with the quantum mechanics. Basically what happened in case of classical mechanics, when there will be barrier in front of electron, the electron will stop over there. That this first diagram, it shows over here. Now here the second one, this is just indicating how the electron movement, it is in the form of wave function. And basically what happened, when there will be a barrier, electron, it moves from this barrier to the next level. So very precisely this tunneling of electrons we have to monitor, and if by using the feedback mechanism. So this tells us that how this quantum mechanical tunneling can be useful appropriately to monitor the surface of any conducting material. This is one another diagram which just indicating how this piezoelectric effect will be important in case of scanning tunneling microscope. You see in this diagram, we have this is the tunneling electron, this is the metal tip, this is the conducting sample is there, and above this conducting sample metal tip is there, and here how electrons can tunnel, how charge carriers can tunnel from this metal tip to the conducting surface. And this using feedback mechanism, tunneling can be easily controlled. So as all of you know, the piezoelectric effect, this is very simple effect, very important effect. And what we do, the piezoelectric crystal that we use, barium titanate over here. Now, once you know the history of AFM, since it is related with the STM, the next very important point comes in our mind, how this AFM is different than the other microscopes. What are the other microscopes? We are having optical and electron microscopes. So how FM is different than optical and electron microscope? Can you hear me? It's okay?
Yes, sir.
Okay. It becomes very important to see this difference. The reason we are having optical microscopes, we are having scanning electron microscopes. So how this AFM is different than the optical microscopes and electron microscope? So these are the some of the points. The first important point is how image formation takes place in case of optical microscope and AFM. How image formation takes place in case of optical microscope. Basically, what happened in case of optical microscope, most of you have taken the images. You have taken the images using the optical microscopes. So basically, one can generate the two-dimensional images. Whereas in case of AFM, three-dimensional images can be obtained. Three-dimensional means you can get the XY direction and Z directions. And one very important point is here, in case of AFM, the resolution of AFM in Z direction is better than the XY direction. So this helps us to easily identify, to detect the depth, that is top and hills, top and valley at the surface level, or you can say the height of any particle, or if there is any pits, the depth of pits can be easily identified, because here it provides us three-dimensional images. As far as its magnification is concerned, in case of optical microscope, you can go up to 1,000 times, or 1 lakh times. Whereas in case of AFM, you can go up to very extremely high level, extremely high. And even this AFM, the magnification in AFM can be comparable. It is far better than the electron microscope, or you can say scanning electron microscope. So because of its very high, extremely high magnification, most of the scientists are preferring AFM rather than optical microscope and electron microscope. Now here, as you know, XY scanning is okay, but the Z direction, that is called the vertical dimension, or you can say it is height of the particle, or depth of any pits or holes, that cannot easily scannable by using optical microscope. Okay. Whereas in case of AFM, Z direction can be easily scanned. So what happened? Whenever you are synthesizing, whenever you are preparing a thin film by any technique, the height and depth of holes or pits that is present over the surface of thin films can be easily identified and measured. As you know, the presence of pits or holes over a surface, it is very important for its analysis becomes very important for the further development of thin film and devices, thin film based devices. Now, one another very important point is there. What is the nature of scanning? Basically, what we do by using optical microscope or electron microscope, we can scan at certain points, or it is also called dimensions of the scanning. The scan can be performed at certain points. You can take some matrix, say for example 2x2 matrix, 3x3 matrix, or 4x4 matrix. Whereas in case of AFM, it uses the raster scanning technique. Raster scanning technique means the scanning can be possible line by line. So what we do, we can start scanning from one end and you can go up to last end. So this technique is very popular in AFM. This technique is available in only AFM and it's called raster technique, raster scanning technique, or line by line scanning technique. So this raster scanning technique, it provides us the complete information of the surface rather than the information at certain points, which is possible in case of electron microscope, scanning electron microscope, or optical microscope. So this gives these features of AFM gives edge over other techniques. Now here, no doubt, the magnification, the raster scanning techniques are there. In spite of all this, there are certain limitations of scanning electron microscope and atomic force microscope. So whenever you will see, if you will compare same with the AFM, so you can say what are the comparison. One more comparison is there. Dimension we have already seen. Here in case of SEM, the high depth field can be obtained. This is the imaging advantage. The high depth field can be possible using scanning electron SEM. Whereas in case of AFM, the high contrast can be possible. So what will be the merits of it? Whenever there is high contrast, very easily we can visualize each and every fits and discs. That is not possible in case of SEM. Though in case of SEM, you can go up to high depth level. But here, in case of AFM, you can go up to high contrast level. So very easily we can identify the particles. Very easily you can identify the defects. What kind of defects are there? Now here, in case of the same measurement, chemical composition can be possible. As all of you know, EDAX technique. Whenever you will couple EDAX technique with same, chemical composition can be known. Whereas in case of AFM, the physical properties of sample can be known, can be possible. As you know, scanning electron microscope, same, it requires vacuum, high order of vacuum. That is what should be the scanning environment. In fact, you can say this is the drawback of the same electron microscope. It requires high order of vacuum. And most of the time instrument system goes out of order because of this vacuum, high order of vacuum. Here there is facility in case of AFM, whereas there is facility in case of AFM that you can perform this scanning, raster scanning in case of AFM by in air, liquids or vacuum. Option is there. So because of this option, we prefer to go for AFM rather than SEM. And one another very important point is there. Whenever you want to use AFM technique for biological samples, most of the biological samples are liquid, are available in liquid form. So you can use AFM technique over there. There we cannot use SEM. So this is the added advantage of AFM technique over SEM technique. With this is the comparison between the optical microscope, electron microscope and atomic force microscope. Now let us see what are the broad areas where we can apply this technique, AFM technique. Because there is need to identify it. Without identifying the various areas, it is not possible to properly use the AFM technique. So one very important area, as most of us are from physical sciences, so all of you know about solid state physics. There are many things to do in solid state physics. And you know the solid state devices, microelectronic devices, optoelectronic devices, power semiconductor devices. We need to design, fabricate and characterize the materials and devices in our solid state physics. So we need to identify the areas. So one very important area in solid state physics is there. Whenever you are preparing material, it becomes very important to know its various properties, its physical properties, chemical properties, optical properties, electronic properties, magnetic properties, electromagnetic properties, electro-optical properties. Because without knowing these properties, we cannot further apply these materials for making the devices. So our main objective is to prepare the material, best quality material, and then to identify their properties. Which property dominates in that particular material. And as per that, you can use that material for device application. And this properties, you can go up to atomic scale level. So using this AFM technique, the properties of solid materials can be easily identified up to its atomic scale level. This is very important. Now here, whenever you are synthesizing a material, you need to identify its crystalline structure. That is crystallographic studies of that material. It is very important. So you can go through this technique. As you know, the electromagnetic properties comes from atomic level. So you can also explore by using this technique. Further, if you will go for semiconductor physics, as you know, most of the devices are semiconductor devices. They are the PN junction based devices, junction based devices. So in semiconductor physics, what happened whenever you are preparing a material, whenever you are preparing junction, in junction formation, the surfaces, the characteristics of surfaces plays very important role. So you need to know before preparation of the PN junction, if you have prepared P-type material, now you want to deposit N-type material over it. You need to know, first of all, you need to know what is the characteristics of surface of P-type material, so that you can go for formation of N-type material over it by using various techniques. So this surface profile becomes very important. Basically, what we do, while preparing the junction-based quality junction, we ignore it. And ultimately, what happens? Whenever you will get its characteristics, IV characteristics, VI characteristics, or other characteristics, it suffers. And whatever you are expecting its result, you cannot get the better efficiency. You cannot get the better result. So that's why in semiconductor physics, very easily using AFM technique, you can get the idea about surface profile of your material, of your semiconductor materials. Another thing is there, in this semiconductor physics, we need to develop the digital integrated circuits, digital integrated circuits, and optical integrated circuits. As all of you know, whenever you will go for integration, there are many things to identify. So using this AFM technique, we can identify how one element is different than the another element. Various things can be scanned up to its high contrast level. So in case of digital integrated circuits and optical integrated, similarly in case of optical integrated circuits, as you know, today optical integrated circuits are the basis of all the photonic based devices like LED, laser, and their proper coupling, means active and passive components and devices. So AFM also plays very important role in synthesizing of or integration of optical integrated circuits. Similarly, another thing becomes very important in case of semiconductor physics. Whenever you want to achieve something different, if you want to achieve better performance, so doping profile must be proper. Whenever you are doping one material, either trivalent material or pentavalent material in your host material, so doping profile must be better. It must be appropriate. So using this AFM technique, you can also get idea about doping profile. Another very important area is there, chemistry. So what we can do using AFM in chemistry, along with the surface, the reaction kinetics can be easily studied. It is very important, reaction kinetics. Those who have read the chemistry, they know about it. The reaction kinetics. And whenever you are having idea about reaction kinetics, no doubt, whatever the product will be there, whatever its properties you are looking for, can be easily controlled by controlling the reaction kinetics. One another very important point is there, polymer chemistry. Nowadays, it has become very important. It is playing very important role for device fabrication, whether optoelectronic devices, electronic devices, semiconductor devices, power semiconductor devices, or microwave-based devices. The polymer chemistry is playing very important role. So what we do in this polymer chemistry, generally we prepare different kinds of polymeric materials. So what we can do, the structure of polymeric compounds can be easily studied using this AFM. Moving ahead, how this AFM can be used for biotechnology. So as you know, in biological samples, if you will go up to its molecular level, it becomes very important to identify each and every molecules. So it is called molecular engineering can be possible by using AFM techniques. Similarly, if you will move ahead in one other area is there. It is very popular nowadays. It is called molecular and cell biology. So what we do in case of this cell biology, molecular and cell biology, using this AFM technique, we can get the images of living cells, cytoskeleton, chromatin, and plasmids. These are the biological terms. So all these things can be possible by using this AFM techniques in cell biology. Not only that, even the elasticity and viscoelasticity of living cells can be known, can be studied. How the crystal growth and polymerization is taking place in case of cell biology. The crystal growth is possible in case of cell biology. That can be studied by using this AFM technique. One another very important area is there. It is called dairy technology. Most of us are very fond about the dairy products. We all are using the dairy products nowadays, every day in our daily stuff. What we can do, how AFM technique can be applied to dairy technology. So one very important point is here, the topographical images of dairy powder particles. Whatever dairy products are there, its images can be easily obtained. One skimmed milk. We all are using skimmed milk. Skimmed milk powder. Milk protein, that is concentrate powders. Its surfaces can be studied. Lactose, crystallization, etc. All these things can be possible. Means, see, AFM cannot be applied only in physical sciences. Can be applied in chemistry, biotechnology, dairy technology, molecular technology, molecular cell biology. One very important area today we are using pharmaceuticals. What we are doing in pharmaceuticals, we are synthesizing and preparing different types of medicine. So whenever you want to study the structure of medicines, basically what pharmaceutical people they are doing, they are designing it, they are synthesizing the certain compounds, they are mixing various compounds together, various elements and materials together, and they are getting certain specific composition, and we call it medicines. So whenever they are synthesizing, what is the structure of their compound? Synthesizing compounds can be studied by using this air. Moving ahead, there are various fields of engineering. As you know, mechanical engineering, electronics and telecommunication engineering, computer science engineering. So AFM can be used in different fields of engineering and technology. One very important area is there. If you want to develop new technology, you need to use the AFM. Not only that, whenever you want to modify the existing techniques or technology, you have to use the AFM over there. So these are some of the broad areas where we can apply AFM techniques for the studies, for the synthesis. So in this way, we need to identify certain specific areas. So let us try to specify certain specific area where you can apply the AFM. One very important compound, natural sciences. As you know, we need to synthesize proteins. It is called protein complexes or assembly of proteins. One example is microtubules. So the structure of protein synthesis or protein complexes can be easily studied by using AFM techniques. Nowadays, we are using nanotechnology. And how we are synthesizing nanoparticles? By adding certain foreign materials in our host materials. So there we need to identify, we need to specify the foreign atoms in our host materials. So it is called identifying atoms of foreign materials in our host materials. This has become very important nowadays, because whenever you want to change the property of certain property of your material, you have to go up to its nanoscale level. When in that nanoscale level, it becomes very important to identify the foreign atoms. Similarly, all of you are aware about the cancerous cells. Nowadays, cancer, it is more number of patients are increasing affected with the cancer. So it becomes very important how to identify which cell are cancerous cells. How you can identify the cancerous cell and normal cells. So this is very important area nowadays. Most of the biological scientists, they are using it, doctors are using, and they are differentiating cancerous cells with the normal cells. So whenever you will do the AFM, the characteristics of cancerous cells will be entirely different than the characteristics of normal cells. So this, because after identification, they can remove the cancerous cell from the body. Otherwise, what will be happen? They can remove the normal cells that is important for the living organisms. Similarly, whenever you want to identify the physical changes in atoms and molecules level, that can be identified by using the AFM technique. Another very important point is there. Nowadays, doctors are trying to study the behavior, shape, and nature of normal cells and affected cells. So it is also possible by continuously monitoring, we can differentiate the cells which are normal cells and the cells which are the effective cells in living organisms. Now, the application area of AFM is quite broad. That's why we need to, being physical sciences students, scientists, we need to specify ourselves. We need to identify certain area. So here what we do, if you will see the surface, if you want to go for surface topology, we need to use the AFM over there. As we have discussed, we can study the chemical properties, addition properties of the surfaces. For chemical scientists, it becomes very important nowadays. If you will go and if you will see in chemical engineering, there for them, the surfaces are playing very important role, because whatever materials they are preparing, it is related with the addition property. So what we do, how this addition properties can be studied by using this AFM. And it is also important for us because we want to prepare the junctions. Whenever we will club together two dissimilar materials. So how they are active for their adhesive property, it becomes very important. So, so for semiconductor scientists, semiconductor engineers, or for chemical engineers, it is very important to know the adhesion property of surfaces. So this we can study by using the AFM technique. One another very important characteristic, it is called hydrophobicity. Hydrophobicity means the property of repelling water rather than absorbing it. We are preparing the surfaces of materials or devices that must not come in contact of the water and environment. It is called hydrophobicity. So it is very important to do it. Similarly, we need to know the thermal transport property, electrical properties of surface, frictional properties of surface, plasmonic activities. What is this plasmonic activities? Basically, what we do, the generation, manipulation, and detection of optical signals along a metal dielectric interface. How it is this plasmonic activity becomes very important for design and fabrication of optical integrated circuits, OICs, because there we use, sometimes we use metal dielectrics, sometimes we use metal based waveguides, sometimes we use dielectric waveguides, or sometimes we use metal and dielectric based waveguides. There it becomes very important to go through the plasmonic activities, how that active and passive components, basically the passive components like optical switches, optical couplers, optical branchers, all these, how they will be sensitive towards the light signal, optical signal. Similarly, using this AFM technique, one can study the interacting forces between the atoms and molecules. Sometimes it becomes very important to evaluate this property. When there is atoms and molecules, how they are interacting with each other, how they are interacting together. So it is called force evaluation, interacting force evaluation between the atoms and molecules. Being semiconductor scientists, we will stick ourselves with the surface property, that is surface roughness, because we want to develop the solid state devices. Solid state devices means diode, transistor, FET, MOSFET, JFET, IGBT. Similarly, microwave devices, gun diode, pin diode, all these. For the development of microwave devices, optoelectronic devices, the surface roughness becomes very prominent, very important. Because this surface roughness, it dominates the surface properties and indicates various kinds of defects and dislocations present in your material, your specimen. That's why manipulation of surface at nanometer level or micro level, it tries to control the various properties. So whenever you want to control the surface roughness at nanoscale level or micro scale level, AFM plays very important role for it. And we have to go through the AFM techniques. Similarly, in case of nanotechnology, nowadays one area has become very popular, and it is called self-assembled area. And it is called self-assembled nanoparticles. So whenever you are going to synthesizing self-assembled nanoparticles, it becomes very important to see their structure. It becomes very important to see how and what is the orientation of self-assembled nanoparticles. So this AFM plays very important role over there to just identify the, the orientation of self-assembled nanoparticles in this area. Because this self-assembled nanoparticles can be used for making the device application. Here, one diagram is there. How we can identify the defects detection, how we can detect the defects in our semiconductor materials. Basically, whenever you are going for the fabrication of devices, preparation of the junction, first of all, it becomes very important to prepare best quality material, semiconductor material. After preparation of the material, you need to identify what kind of defect it is. What is the level of defect? Once you will be identified the defect, then you can plan how to overcome it. Because directly you cannot go for the development of devices. The identification of defects plays very prominent role in semiconductor technique, semiconductor area. So here this diagram is just indicating how the AFM tip of how the AFM tip can identify the defect area, defect label, and the defect volume. So these two diagrams are just indicating the label of defect, site of defect, and the volume of the defect in your semiconductor material. And then accordingly we can go through, we can use the various techniques to overcome the defect. So identification becomes very important over here. Here, this diagram, it indicates, it is the line profile analysis that shows the vertical dimensions along one chosen scan line. Suppose you have prepared material and you are going through the AFM technique. So here, what is the level of defect? What is this level of roughness at the surface of your material? So this can be known through this profile. It is called line profile analysis, and this signal it generates through the AFM technique. Here, this is the one diagram. This indicates what is the volume of the defect. It is just indicating this. The shaded part is indicating what is the level of defect in your material, or it is also called the calculation of the volume and area of the missing features that is scanned by the AFM technique. So whenever you are preparing material, you have to go through these techniques, and whenever you will go through these techniques, various kinds of defect area, defect points, defect volume, or missing atoms, missing molecules, the shape, orientation of atoms and molecules, the crystalline orientations, all these things can be studied. And whenever you are having all these information, that materials can be further, you can further proceed for the device fabrication. We can prepare the best quality junctions, we can prepare the devices, we can go for integration of the, either you can prepare digital integrated circuits or optical integrated circuits. So these are the various areas that we have identified where you can apply the AFM technique. Now let us see what is the instrumentation part of this AFM technique. So if you will see this instrumentation of this AFM technique, So basically, it is similar to the STM, scanning tunneling microscope. Here we use one tip. It is called cantilever. It is a cantilever. Basically, what we do in case of this AFM, it is a basically we measure the force interaction between the cantilever and the surface. And using this force, interacting force between the cantilever and the specimen surface, you can study the various properties of the surfaces. So what we use one tips. It is called modified tips. We use some software. It is called adjustment software, and we use feedback loop as we have seen in case of STM. In case of STM, we were using the tunneling current can be easily controlled by using feedback loop. So here this feedback loop is also important over here in AFM. And here one very important point is here. If you will see this diagram, can you see this diagram?
Yes, sir.
Okay. If you will see this diagram, here we are using AFM sample stage, and here we have written sample. Means this stage, this is XYZ stage, because we have seen AFM can be used for XY and also Z also, and we have seen the resolution of AFM will be better in Z direction rather than XY direction. So that's why the hills, the height, or the valley means bed depth can be easily scanned. So now here this cantilever, it plays very important role. Cantilever, this connected with the tip. This tip, it should be as sharp as possible, because we want to go up to atomic level. The tip of your cantilever must be very sharp. But the most important part is here. Here we are using detectors. They are called position sensitive detectors. There are 4 detectors: A, B, C, and D. Okay, and one laser source. So basically, what is happening here? Here this cantilever is attached with the tip, and whenever you will proceed, whenever you start, generally this AFM scan the sample, and it is called line by line scanning. It is called raster scanning. It starts from one end and finishes up to another end, and it is called raster scanning. So whatever this deflection between whatever deflection will be there between the tip and the sample, this deflection can be easily identified by using this laser source, light source. And this laser light, basically it is falling over tip. So as deflection is taking place, this deflection is identified, it is detected by the 4 detectors. They are called position sensitive detectors: A, B, C, and D. So the working principle is quite simple. But here in this AFM technique, how to adjust the instrument, it is a little bit important, because this tip should be properly fallen over surface of your sample. So here only 4-5 steps you can operate this AFM in 4-5 steps. The first step is cantilever deflects due to atomic interaction between tip and sample, and this is converted into electrical. It's a equivalent electrical signal. So whatever interaction, whatever deflection is there between the tip and sample, that can be converted into its equivalent electrical signal. Another very important point is beam positions on the arrays of this position sensitive photo detectors is converted to an electrical signal in terms of voltage. Another step is there, you can monitor the positions of cantilever using the laser and photo detectors. So how this lever is bearing, how this lever is deflecting, this can be easily continuously monitored by using this laser beam and the photodetectors. Laser beam and photodetector. Now what happened? When this detector, we are using array of detector. This is assembly of detector. Means we have combined 4 detectors together. A, B, C, and D. So this, when this light ray falls at this AB detector, it gives vertical bending of the cantilever topography. Means detector A and B, it is responsible for vertical bending, whereas detector C and D, it gives the lateral bending of the cantilever. So in this way, by observing vertical bending and this lateral bending, we can completely scan all the bendings, all the movements between the cantilever and the samples. The same diagram is shown over here. Okay, this you can see over here. This diagram is just indicating. Here this is the laser beam, cantilever, and this here the tip and the surface. So this tip and surface, this whatever deflection is there, whether it is vertical deflection, whether it is lateral deflection, can be easily identified by your array of detectors. Detector AB, detector CD. Okay, so in this way, if the array of detectors are very sensitive, okay, I think all of you have read about the different types of detectors: pin diode, pin photodiode, PIN, avalanche photodiodes. Okay, in which avalanche multiplication takes place. Avalanche multiplication takes place.
Yes.
So using this sensitive photodetectors, array of sensitive photodetectors, the whatever deflection is there between tip and sample can be easily measured in this AFM technique. This is one another diagram how this feedback technique, because feedback technique is important, how this feedback technique can be used to convert this deflection physical movement of tip into its equivalent electrical signal. Okay, here this diagram is indicating what happened when the tip and surface distance moves. So one potential is called, it is called Lennard-Jones potential. That potential can be observed over here. Lennard-Jones potential. Next thing becomes very important over here. What are the steps of operation of the AFM? So here, for measurement of extremely high resolution images, we need to become the master of this AFM. We need to become the we should be able to operate AFM properly. So how we can operate the AFM? So these are some of the steps. First of all, place the sample on the AFM stage. See the stage, the placement of your sample should be appropriate. If the placement of sample will be not appropriate, there will be no proper focusing of laser beam. So first, this is the first step. Place the sample specimen at proper place. Okay, and set the probe properly. It is very important. In third step, put on the laser and align it towards the specimen. Generally, what we do, most of the times we do mistake over here. Okay, you are placing the specimen sample. Okay, you are putting the probes over there, but if you will not focus properly the laser beam, it becomes very difficult to measure the deflection between the cantilever tip and surface. This third step becomes very important over there. The focusing should be appropriate. For this focusing, the laser beam that you are using must be very pinpointed, must be very narrow. And in fourth step, align the photo detectors properly. Because what is happening? In earlier diagram we have seen, whenever you are falling laser beam over your cantilever, and after reflection, this laser beam is detected by the array of detectors A, B, C, and D. So the alignment of photo detectors must be proper. So basically this part is easier because the photo detectors are linked with this your AFM. So there is we do not have option to move it, but you have to take care. Next point becomes very important in its scanning. They set the parameters properly. Basically nowadays AFM are coming, they are the automatic software coupled with the automatic software. So whatever parameters are there, you need to know the range of parameters and you have to give appropriate range. Otherwise what will happen? It will become very difficult to scan properly. So whatever the parameters are there, you need to know the range of parameters, and by putting appropriate value of the parameters, you can easily scan it. And then finally, very safely after scanning, one thing is also important here, the rate of scanning. Here I would like to suggest here, whenever you are going for AFM, don't be in a hurry. Don't go for faster scanning. The rate of scanning must be slow. Because when there is slow scanning, it will be appropriate. You will get better resolution. If you go for very fast scanning, generally what happens, we always, most of the times we remain in hurry and we just put the sample and we set it for fast scanning. That is not good. It will damage the tip. Tips are very sensitive. We must take care about it. So we need to go for slow scanning rate. Whenever you will use the slow scanning rate, resolution will be far better. And if resolution is better, you will get best picture quality. You can easily identify each and every atom. You can even count. You can detect the defects. So that's why the scanning rate must be slow or moderate. Must not be very fine, very high. And after scanning, safely retract the probe from the sample. This is very important point. Here we need to take precaution. Very safely we have to retract the cantilever from the sample. So these are the some of these steps. If you will follow these steps, very easily you can operate the AFM. You can scan it. You can get better picture quality. Otherwise, there will be problem. Here, this is the working of AFM, as we have described over here. Okay, this we have already discussed how it works. What are the steps that you have to follow? Okay, these are the van der Waals force that works between the tips, cantilever, and the surface. Electrostatic forces works over there. Now here, since in this AFM technique, tips becomes very important. So we need to know certain things about the tips. Because as you know, the AFM tips are very costlier. And most of the times when we are doing AFM technique, AFM scanning, the tips goes out of order. So we need to know certain things about the tips. So generally the tips are made of silicon nitride. Okay. Why? What is the reason? What is the characteristics of anybody can tell something about silicon nitride? What are the characteristics of silicon nitride? Silicon nitride. As you know, silicon nitride, it is hardest material. Silicon dioxide, silicon oxynitride, and silicon nitride. So basically, the silicon tip, the cantilever is used the hard material. Okay. So generally for this hard samples, when your sample is hard, see we are having the samples of specimen of different nature. Few materials are hard, but whenever you are using biological samples, they are very soft. We have to also take care that for biological samples, the tip should be softer one, not the harder one. But if your material, if your sample is hard, then you can use the hard tip. Basically, it is made of silicon nitride. Okay. So we have to take care about it. One thing is that the dimensions of the cantilever are set after carefully considering the spring constant, because spring constant is important over here. And this spring constant requirement vertical and lateral direction. Okay. This we have seen. This principle of atomic force. This we have seen. Okay. Here we have to see what are the various advantages of atomic force microscope. So one very important point is there, easy to prepare samples for observation. We have already seen the comparison between the optical microscope and atomic force microscope, electron microscope and atomic force microscope. So here one very important point is there, in case of whenever you are going through the AFM technique, it is very easier to prepare the samples. We have we have also seen this AFM we can perform in vacuum, air, or in liquids. These are the techniques that we have already seen. These are the points that we have already discussed. Now these are the some of the points that tells the challenge. What are the challenges in the way of AFM? What are the challenges that you have to encounter? The first challenge is very sharp probe must be constructed so that the high resolution image can be obtained. This is the first and most important challenge in front of us. Your tip is very sharp and its resolution depends upon its sharpness. This is the reason that the cost of tips are higher. It is little bit more. And to get the probe within the scanning range, this point is also important. As I said, whenever after doing all these things, whenever you are going for scanning, you have to give certain parameters. The parameters must be appropriate within the range. So this is the second point is very important. To get the probe within the scanning range, the surface control panel must be proper. All these things are there that you have to take care. The force transducer must have force resolution less so that the probe is not broken while scanning. Certain transducers we are using, it should be appropriate. The feedback controller that permits rapid control so that the probe can follow the topography on the surface must be created. There should be proper feedback mechanism, proper feedback control. Otherwise, it will be very difficult to get the signal from the AFM. Here we use XYZ piezoelectric scanner that has linear and calibrated motion must be used. So whatever piezoelectric scanner we are using must be calibrated properly. We need to use the high speed computers that can display the images in real time, because here we are observing the real time images. Your system should be faster. Now here, what are the certain disadvantages of atomic force microscope? We need to also identify it. Okay, it can only scan a single nano size image at a time of about 150 to 1 nanometer. We have to take care about it. Now, low scanning time. Okay, and because of this low scanning time, it creates thermal effect, thermal drift in your sample. The tip and the sample can be damaged during detection. This is very important point. This becomes most important when we are using the biological samples, because our biological samples are very soft. They are very, very soft. So while applying the pressure, we need to calibrate it. We need to take care that it should not damage the sample. And finally, this AFM, it has limited magnification and vertical range. So these are the disadvantages. Next thing becomes very important. What are the various modes of operation? In which modes we need to operate our AFM? And which mode will be more better? So there are three primary imaging modes in AFM. One is called contact mode, non-contact mode, and intermittent mode. That is called tapping modes. So basically what happens in these three modes: contact mode, non-contact modes, and tapping modes. So here in contact mode, as it is well clear from its name, in this mode, the tip is constantly in touch with this sample surface. When tip will be continuously in touch of the sample surface, it is called contact mode. And here what we do, the applied force is kept constant while the tip scans the surface, creating the surface images. Now what is the advantage of it? This mode is good for samples with a rough and rigid surfaces, and it provides fast scanning with high resolution. So this mode can be useful for solid state physics, because what happened in semiconductor technique, whatever surfaces, whatever thin films we do prepare, its surface remains rough. So for this type of surfaces, for this type of specimen samples, whenever you are using AFM, it must be in contact mode. One can use in contact mode, because here this surface is rougher surface. It is not completely smoother surface. So you can use AFM in contact mode. So what will be the advantage? It gives faster scanning. It provides fast scanning, and you will get better resolution. But what is the demerits of this mode? The soft sample like tissues can be deformed or damaged due to this applied force. Okay, and this drawback can be overcome by measuring this sample in aqueous environment. Okay, suppose there is one biological sample, and if there is no facility of AFM in other modes, non-contact mode, so how we can overcome it? The AFM can be taken in aqueous environment mode. Okay, so it will reduce the interaction force between the tip and the sample. So what will be happen? It will prevent the damaging of the sample. So each modes are having their own merits and demerits. So this is about contact mode. Now here, what is this non-contact mode? So basically in non-contact mode, there will be no contact between the sample surface and the probe. And basically what happened? The probe oscillates above the sample surface, forming a weak attractive force between the tip atom and the sample surface atom. So a force will act, attracting force will act between the tip and the sample. And whenever you will measure this attractive force between the tip and the sample, we can scan the sample in this non-contact mode. Now here, basically what happened? Here the feedback signals are obtained by measuring a frequency shift in the mechanical oscillation by the cantilever. So what are the advantages and disadvantages of this mode? The force exerted on the surface sample is very low in this case. Moreover, as there is no contact between the probe and the surface, the probe lifetime can be increased. This is the advantage of non-contact mode, because there is no direct contact between the probe and the surface. So the lifespan of cantilever can be increased. The lifespan of the tip can be enhanced. Now here, another very important point is over here. There is possibility in this mode to observe an atomic defect. Okay. Whenever the big attracting force between the tip and sample can be observed, and if any kind of atomic defect is there, as all of you know about atomic defect, line defect, volume defect, surface defect. So if there is any kind of atomic defect is present in a sample, that can be monitored, that can be observed by using this technique. Now, along with this advantage, there will be certain drawback of this non-contact mode. So what is the drawback? The drawback is low resolution and it requires ultra high vacuum, because this is the non-contact mode. So in this non-contact mode, it requires the ultra high vacuum. This is the drawback. Whereas in contact mode, there is no need to go for high vacuum. There is no need to, within the air you can do the scanning. And here in this non-contact, since there is no contact between the tip and surface, so resolution will be lower. So low resolution can be achieved over here. So what will be here? The image quality will be lower in this mode. Now third mode is called tapping mode. What happened in this tapping mode? In this tapping mode, the tip is not in constant contact with the sample surface. Instead, the cantilever is oscillated at its resonant frequency, which makes the tip lightly tap on the surface during the scanning. Here there is no, we have seen contact mode and non-contact mode. And in this tapping mode, there is no, neither it is contact mode nor in non-contact mode. It is just oscillating. And with this oscillation, you can monitor the surface. Here what happened? A constant tip sample interaction is maintained by monitoring the oscillating amplitudes and an image is obtained. Several parameters that affect the image contrast are the height, phase signal and amplitude. Okay. And phase signals are influenced by material properties of the samples. For example, viscoelasticity, the force during scanning is greatly reduced. Therefore, this mode is useful for biological samples, where the samples are easily damageable or loosely bound to their surface. So this tapping modes can be used for biological samples. If you are having biological samples, this you can operate AFM in tapping modes. So in this, now what is the drawback of this mode? It is very slow scanning. Since neither there is contact nor there is non-contact, it is in tapping mode. That's why the scanning rate will be slow. So it is very slow scanning. So in this way, whenever you are operating AFM, You can operate either anyone out of these three modes: contact mode, non-contact modes, and tapping modes. Each modes are having their own merits and demerits. Depending upon the quality of samples, the types of samples, one can select a particular mode of operation of your AFM. Now here this diagram is just indicating here. This is just indicating whenever you are synthesizing a thin film or any material, you need to know a little bit about its surface quality. You need to know a little bit about its thickness. Because what happened, if you will go directly for this AFM measurement, AFM scanning, then it will become very difficult to set the parameters. That's why if you are going through, first get the information about its thickness. What is the thickness of your sample? What is the order of thickness? Whether the surface is rougher surface or a smooth surface. So this is one thickness profile. We have designed and fabricated. We have synthesized aluminum doped zinc oxide thin film, and we have taken its thickness. We have measured its thickness by using ellipsometer, thickness and refractive index. So just go through its thickness. If you will see here, thickness is given 323 angstroms. You can get the thickness profile. You can get the average thickness. So in this way, if you are having this type of information, then directly you can go for AFM measurement. So now if you will see, we have synthesized the thin films of different layers, say for 5 layers, 10 layers, 15 layers, and 20 layers. And here you will get this thickness profile. Thickness are different. So at least you are having one rough idea in your mind what is the quality of samples that you have synthesized by using one particular technique. Then you can go for its AFM measurement. At the same time, whenever you are going through the thickness measurement, you know, thickness of any sample, it is also related with its refractive index. So what is the refractive index profile? How the refractive index, now here it is just indicating how the thickness is changing, or what is the variation of thickness of your deposition. Okay, generally this is the major problem in case of thin film preparation, deposition of thin films. Whenever you are depositing thin film, either using vacuum technique or by using PLD technique or by using any other sol gel spin coating methods or LPCVD technique. So what happens, generally the film's thickness should be uniform. So that's why after preparation, after deposition, after synthesis, after preparation, you need to know what is the thickness profile of your sample. Similarly, what is the refractive index? How refractive index distributed? How refractive index varies of your sample? Okay, so this is the refractive index profile of aluminum doped zinc oxide thin film of different thickness, and it is 5 layer, 10 layer. Basically, this refractive index profile has been taken by ellipsometer. Here, this is the 2D and 3D images of aluminum doped zinc oxide. We have synthesized aluminum doped zinc oxide thin film of of 5 layers. We have taken 5 layers and see the AFM images. Can you see it? Can you see it? Yes, yes. Can you see it? None of you are responding.
Yes, sir.
Okay. Can you see this AFM image?
Yeah, it is visible.
Yeah, it is 2D and 3D images.
Yeah.
Now, see this image and observe it. See how the hills and valleys are there. It is here in its two-dimensional image.
Yes, sir. We can see it.
Yeah, can you see?
Yeah, sir.
So, can you see whether can you observe the surface roughness? Can you get the idea about the surface roughness, uniformity, distribution of atoms and molecules? Yes. and now it is more visible in three-dimensional image. Can you see the hills and valleys? Yes, yes. Density of the molecules means distribution. Okay, all these information can be obtained over here. Yes, yes. This image, this is aluminum dope zinc oxide thin film. Okay, aluminum dope zinc oxide thin film. And here we have taken the aluminum is 2 atomic percent. It is synthesized by using sol gel spin coating technique. And here baking temperature was 100 degrees Celsius. And we have annealed the thin film at 450 to 500 degrees Celsius for 1 hour. See, this is the 2D and this is the 3D. Okay, so one thing is very clear, how the orientation is there, how the atoms and molecules have been oriented. It is well clear from it in this 2D and 3D. Right? Yes, can you see this picture? Okay, how the laminar orientation of the atoms and molecules of aluminum dope zinc oxide thin film. So this is because of its high resolution. It is not possible to get this type of information using optical microscope, scanning tunneling microscope, and the same electron microscope. This is possible. This type of image is possible only in whenever you will go through AFM technique. See, very clearly, it is just indicating how the distribution of atoms and molecules are taking place in a proper way. Okay, this is another AFM images, 2-dimensional and 3-dimensional images. This is about 10 layer and 20 layer aluminum dope zinc oxide film, and its thickness was 10 layer and 20 layer. Now you see the surface roughness and all these can be easily calculated, measured, observed by using these AFM techniques. Okay, we have synthesized some of the aluminum dope zinc oxide thin films. Here this table is indicating how the thickness, refractive index, energy band gap, Woodbridge energy are the function of its thickness. Here thickness we have measured in terms of number of layers. Okay, see how this thickness has increased from 144.89 nanometer to 386.20 nanometer, and accordingly its refractive index and energy band gap has decreased. This is one another 2D and 3D image of aluminum and indium. Here what we did to change the characteristics, especially energy band gap of zinc oxide thin film, along with this aluminum, we have added indium. So this is the aluminum and indium dope zinc oxide thin films, and the thickness is 10 and 20 layers. See how as you will increase the thickness, see thickness, how the roughness will be improved. Okay, how the roughness will be improved. So here we can say that to understand the surface morphology, surface texture and roughness, grain size. Okay, so what are the important parameters? Surface morphology can be observed, surface texture and roughness can be observed, grain size can be calculated, distribution of the atoms and molecule, distribution of particles can be studied by using this 3D AFM images in aluminum dope zinc oxide thin film. So see, these parameters are very important: surface morphology, surface texture and roughness, grain size, distribution, particle distribution. Okay, these are very important parameters, can be studied. Now if you will see here, we have synthesized the aluminum doped zinc oxide thin films of varying thickness. So what we have observed? We have observed that the surface roughness decreases with increasing number of layers. Okay, very important conclusion, that as the thickness of thin film will be increases, the roughness of thin film can be decreases. So this can be this conclusion we have made by using this AFM technique. Now if you will see the structure, what is the distribution? It is column-like structure. Column-like structure being observed with 30 layer films. As the number of layer increase, the surface becomes void free and smooth. Okay, this we have observed using AFM technique. And if you will increase the thickness of your thin film, the void and roughness will be decreases. And you can calculate the root mean square RMS grain size decreased from 0.162 micrometer to 0.141 micrometer with increasing film thickness, while the surface roughness decreased from 189 nanometer to 46 nanometer. So in this way, we have just observed, we have gone through AFM technique of different films of different layer, and we have observed this. Now, next very important point is how AFM technique can improve the device's performance. Okay, devices performance. So, as you know, this AFM technique, it plays very crucial role in capturing and converting light into electricity. Devices, different types of devices can be used. We can use photodiode. We can use this AFM technique for battery, development of batteries, development of photo cells, photovoltaic cells, solar cells. You can use this AFM techniques for various samples. You can study the morphology, electrical property, magnetic property, chemical property of your samples. So here we have tried to show how this AFM technique can be improved, can be used in different fields. In the field of optoelectronic devices like photovoltaic cells, photodiodes, development of photodiodes, development of photovoltaic cells, development of lead sign laser, development of batteries. Okay, and by using this AFM technique, how you can improve the performance of these devices: lead, laser, PN junction diode, transistor, how performances can be improved. AFM in electronic devices. Whatever electronic devices are there, you can apply. AFM technique in electronics and energy materials. Okay, so in this way, we can apply, one can use the AFM technique for observing the various properties of surfaces of your thin films. Since the development of devices are based on thin films, formation of thin films, quality of thin films. So no doubt, by using appropriate using of AFM techniques, the performances of photovoltaic cells, the efficiency of your photodiodes, LEDs, lasers, batteries can be enhanced, can be improved by using the AFM techniques. Now here, our next very important point is factorial and multi-factor. Whenever you are having this two-dimensional and three-dimensional images, if you are having data, you can go through the further analysis. So it is called factorial and multi-factorial analysis. This is possible whenever you go through any software. What is this factorial and multi-factorial? Whenever you will see the surfaces only you can get the information what is the surface profile. We will not get the better analysis about its, or very clear and precise analysis about its value, like what is the height of crest, what is the height of trough, what is the distribution properly. So whenever you will go through the factor and multi-factor, if you will go through this type of analysis, factorial analysis and multi-factorial analysis, all these things can be known. So let us come to the conclusion of this technique, AFM technique. As you know, AFM is a powerful technique for scientists to have an insight in membrane biophysics, and you can go up to its micrometer and nanometer range. The ability to image, one can be able to get the image cell surface at very high resolution. This we have seen. The resolution is far better in case of AFM techniques. It provides 3D surface profile of conductive as well as non-conductive samples. No doubt whether whether your specimen is conducting or non-conducting, that is doesn't matter, and we can scan it by using the AFM technique. The ability to AFM is having ability to operate in liquid and ambient air. It has allowed to map many different samples properties up to its nanometer, micrometer or nanometer range. It can be used, AFM can be used in different streams of science and technology. As we have already identified the areas, broad area where you can apply the AFM techniques. One very important area is there, detecting major and minor group dimensions of DNA. Molecular scale ordering and properties is possible in case of polymer interfaces. Atomic stiffness in organic and inorganic crystals and its change at defect site. But whatever atomic stiffening is there in case of organic and inorganic crystals, that can be easily monitored. Detecting major and minor groups dimensions of DNA. Okay, this we have already seen. Here, polymer, the properties of atoms and molecules in polymer interactions. This we have seen. Okay. And recently there have been some progress in improving AFM scanning speed resolution. And for example, high speed AFM. Now we are also having high speed AFM, high resolution AFM. That is called HRAFM and HRFM and high resonance frequency FM. So to improve the speed, resolution and resonance frequency, we are having, one can use the HS-AFM, high speed AFM, high resolution AFM and high frequency AFM. Now AFM is also combined with several techniques such as fluorescence microscopy to acquire more efficient data. The potential improvement of AFM will enhance the possibility to apply this technique in a wider range of biological fields. So one can, if you are having biological samples, you can connect this AFM with the fluorescence microscopy, so you will get better results. Now, thank you very much. With this, thank you very much.
Thank you, sir. Any participant has any question, please put it on the chat box.
There are 3 questions in the chat box.
Yes. Yeah, please ask.
How is AFM used in nanolithography and surface modification?
Okay, as we have seen that nowadays AFM is playing very important role for nanotechnology. What happened in case of nanotechnology? Whenever you are synthesizing nanoparticles and if you are doping it, one thing becomes very important to identify the foreign particles, dope particles. So you can do it. There is no problem at all. So this AFM, because of its very high resolution, whatever you want to do, if you want to go for surface scanning, if you want to go for this uh, peaks, height, if you want to go for its valley, whatever peaks and valleys are there, distribution is there, all these can be studied. Even orientation, how the nanoparticles has been oriented, that can be studied, can be scanned. Yes.
Thank you, sir. Another question is how in AFM how patterning is done at nanoscale.
Okay. So here we have seen one very important diagram we have seen. We have seen in case of aluminum doped zinc oxide thin films, as if you will increase the film thickness, the orientation can be easily achieved. One diagram we have seen, very important diagram we have seen, how this AFM technique has useful for the observing the orientation of the particle, atoms, molecules. So in case of nanoparticle, whenever you are synthesizing nanoparticles, how its orientation will be there can be easily observed. Yes.
Thank you, sir. Anyone else has any question? If anyone has any doubt, please write it on the chat box. Otherwise, we'll continue.
I don't think there are more questions now.
Okay. Thank you very much. Thank you.
I think that's all, sir.
Thank
Thank
you.
you very much, Dr. Pandey, for giving an excellent talk on atomic force microscopy techniques. You covered the working principles of AFM, its modes of operation, analysis of images, applications, and you also explained what is the difference between electronic microscope and AFM. Thank you very much, sir. I hope your talk might have helped the students and they will use it in their future endeavors. And we thank you very much for sparing your valuable time with us and sharing your knowledge with us.
Thank you, madam. Thank you very much. Thank you. Okay, madam.
Thank you very much, sir. Panda sir, thank you.
Thanks, sir. Thanks. Can I leave, madam, now?
Just a minute.
Oh. Thank you.
Sir, we would like to share a token of respect to you. Just a certificate.
सर मुझे दिख नहीं रहे. I cannot see, sir.
I think he has left service. Okay, participants, now we move on to the concluding part of this. We would like to share a feedback form with you. I will put it on the chat box. It is compulsory to fill the feedback form for attaining certificate. And now if anyone wants to share something, can share for a minute about your experience in the workshop.
Video audio is on now. You can just switch on your video and audio. If you wish to speak, you can speak now. The rights given to all. Anyone can unmute, speak also.
And there will be one photo shoot also. After
Good
5 minutes.
afternoon, ma'am. Am I audible?
Yes, Mr. Manish, you are audible now.
Afternoon, sir. I'm Manish Khare from Pune, and I wish to say that this opportunity of this workshop was an excellent opportunity, although I came to know about it at the last moment. But thankfully, there was sufficient time and I could register it. And all the sessions were highly insightful, and many things which due to lack of exposure to the field were just like for the we have heard the name but we were not knowing all the nitty-gritties, and all the sessions, let it be of Aki Pandey sir, let it be of Hitesh Mishra sir from MMV BHU, or any other session in Vajpayee sir of the first inaugural session, everyone was so excellent, and they were so impactful that of course I'm not very advanced researcher in the field, in this field, but yes, I'm sure that at any stage, if I get stuck in my research, or if I get stuck at any stage in any work, and I would get back to them for any clarification and explanation, they would be more than helpful, I'm sure. But I just want to thank the organizing team also for organizing such an insightful series of lectures during this workshop. Thank you so much. Thank you so much for giving me this opportunity to express my indebtedness towards the speakers and towards the organization. Thank you, sir.
Thank you, Manish ji. Thank you. It gives us an inspiration if our participants are satisfied to again do such workshops and symposium. Anyone else need to speak? Want to speak? Someone has written on this. Neetu Ashokan, very, very informative. This workshop gave many insights on NWR AFM. Thank you, participants, for appreciating. Now we move on to the next thing. I request Dr. Manisha Singh, organizer of this national workshop, to kindly give a summary of the workshop.
Thank you, Dr. Rinku Bhatia, for giving me opportunity to summarize 1 week national workshop and on advanced synthesis and characterization techniques. So, with proud privilege, I want to say that the workshop received an overwhelming response from all over nation. Participants from nearly 25 institutes spread out in different states like Maharashtra, Gujarat, Punjab, Chhattisgarh, Madhya Pradesh, Haryana, and Uttar Pradesh are participating in this workshop. So inaugural session for the workshop was on 8th August, and it was marked by the presence of Honorable Pro-Chancellor, Lieutenant General V.K. Sharma, AVSM. He's a Pro-Chancellor of MIT University, Madhya Pradesh. And the chief guest of the session was Vice Chancellor Jharkhand, Professor Pramendra Bajpayee. In his opening remark, Lieutenant General V.K. Sharma talked about the importance of synthesis and the characterization technique in designing the new materials of importance. That is, importance, I mean, device applications. So he emphasized on designing and development of new materials tailored for the specific applications. Then in coherence to the Pro-Chancellor Lieutenant General V.K. Sharma, Professor Pramendra Bajpayee, he congratulated organizers for the topic chosen for the workshop. Further, Professor Pramendra Bajpayee in his address emphasized on focus of the research should be towards problem solving rather than sticking on to the publication, project, and patents. Overall, the workshop was planned with the eminent speakers for 9 sessions. In the session 1, Professor A.K. Singh from IIT BHU gave the comprehensive details of the advances in X-ray techniques So the session was evidently visualized by appreciable participation of the participants in question answer session. Session 2 was taken by Dr. Hirdesh Mishra from Department of Physics, Banaras Hindu University. He talked on the basics of fluorescence spectroscopy in applications. Session was very interactive. Session 3 was taken by Dr. Anupma Chandra, Assistant Professor, Dr. H.S. Gaur, Vishwavidyalaya, Central University, Sagar. And the session was on the thin film synthesis. So we can see the session kept the audience or participants captivated, and there was a good participation of the audience. Session 4 was on quantum computing, taken by the Professor Pankaj Srivastava from ABB IIITM Gwalior. He introduced the participants to the advances in quantum computing. The participants were excitedly questioning to the understanding of working of the quantum gates. It was evidently visible in the session. Session 5 was taken by Professor Jay Singh. He discussed in details scanning microscopy, transmission electron microscopy, analysis techniques with the help of different cases. Session 6 was taken by Dr. M.S. Anwar from Dr. M.S. Anwar is a principal scientist of CSIR, Institute of Minerals and Materials, Bhubaneswar, and he talked about the Rydberg analysis. Then session 7 was designed for VSF techniques, and it was taken by Professor M.P. Sharma from Guru Ghasidas Central University. Session 8 was on NMR techniques, and Dr. Manasvi Ghosh, Assistant Professor Physics, Banaras Hindu University, was the eminent speaker on NMR techniques. Then session 9, that is on 14th August, was the last session, and it displays the details of AFM techniques, including instrumentation and applications. The beautiful images of AFM made the participants visualize the resolving power of the AFM. So this is all regarding the workshop. Thank you, Madhvi ma'am, Rinku ma'am, for giving me this opportunity. Over to you.
Thank you very much, ma'am, Dr. Manisha ma'am, for sharing a comprehensive report of the proceedings of this national workshop. Now I request Dr. Pankaj Mishra, organizer of this workshop, to give vote of thanks.
Thank you very much, Rinku ma'am. Good afternoon, everyone. I am thankful to the Honorable Pro-Chancellor, sir, Vice Chancellor, sir, and Pro-Vice Chancellor Research and Director Asset for giving us the opportunity and guidance for organizing this workshop. I am highly grateful to the esteemed Chief Guest of the inaugural session, Professor Dr. Pramendra Vajpayee, Honorable Vice Chancellor, Jayaprakash University, Chhapra, Bihar, for gracing us with the presence and sharing us profound knowledge and setting a right tone for this workshop. I am thankful to all the esteemed speakers who took the pain and gave important insights, various aspects of the advanced synthesis and characterization techniques. I am thankful Professor Dr. A.K. Singh from IIT BHU. He highlighted the particular topic on advances in X-ray technique. Dr. Hirdesh Mishra, Department of Physics, BHU, topic straight of the spectroscopic technique. Dr. Anupama Chandra from Dr. Hari Singh Gaur, Vishwavidyalaya. She discussed on the topic of thin film synthesis technique. Professor Dr. Pankaj Srivastava from Atal Bihari Vajpayee IIITM Gwalior. He discussed about quantum computing. Professor Dr. Jay Singh from Guru Ghasidas Central University, Bilaspur. Dr. Mohammad Shahid Anwar from CSIR, Bhubaneswar. Professor Dr. M.P. Sharma from Guru Ghasidas Central University, Bilaspur. Dr. Manasvi Ghosh from Department of Physics, BHU. Dr. R.K. Pandey from the Central University, Bilaspur. We are thankful to all esteemed guest speaker, and for especially I am thankful to Dr. Manisha Singh, convener of this particular workshop. She worked day and night to organize in the listening with the speaker and overall working in terms of management and coordination for work done by ma'am. Thank you very much, Manisha ma'am. I am thankful to Dr. Rinku Bhatia ma'am for especially comparing and highlighting the facts, timely update and all. Thank you very much, ma'am. I'm thankful to Dr. Madhvi Dhingra, ma'am, for highlighting the particular work in terms of especially the certificate designing, comparing the part includes all IT arrangement. I'm thankful to Dr. Nasir Khan, sir, for especially highlights in terms of the particular support. I'm thankful to Dr. Narendra Kumar Garg, sir, for a particular sharing the thoughts in terms of highly input for this particular workshop. I'm thankful to Dr. Sunil Goyal for media coverage and particular part of this. So I'm thankful to all faculty members of ASET, those who directly or indirectly supported in this particular event. Especially, I am thankful to all participants of this program who are continuously in touch and they just try to learn something new in terms of advanced technology and techniques. So this workshop become a grand success. Thank you very much. Now, have a great day.
So we can have a photo shoot. We can ask everyone to kindly switch on the
Yes,
camera.
ma'am. I request everyone, you just please switch on your camera so that we can just take a photograph.
Request all the participants to switch on the camera, your video for a group photo, please.
All the participants, kindly switch on your cameras.
Participants, request you just for a minute. We want to have a group photo. Ma'am, you can take the screenshots, I think so. Others are not turning on. Of screen 1 and 2 both.
Is it done?
Madhvi ma'am, switch on your camera.
Is it done, sir? Should we move
Yes.
forward?
Yes, ma'am. Thank you very much. Done.
Thank you, everyone.
Thank you, everyone, for your patient listening in all the sessions and being with us. So with this, we come to the end of 1 week national workshop on advanced synthesis and characterization techniques. And I hope you will again be with us in our future endeavors. Thank you, everyone, and have a good day. IT host, you can close the.
Thank you, teachers.
Thank you.